So our last speakers of these sessions and also the VMCAI' is Nick Waddoups. Yeah, he's going to talk about probabilistic verifications of modular net-on-chip systems.
All right. Well, thank you. Well, yeah, I'm Nick, so I also know that I'm probably the last thing before some of you going home or going back to your hotel for the last time, so hopefully it'll be a good one. All right, so as a quick introduction for what we're going to cover today, I'll just briefly introduce the problem space. We'll talk about what on-chip networks are and our motivation for the probabilistic verification that we are doing. And then we'll move into talking about the modular network on chip model that we have developed. And we'll talk about our verification methodology, and then we'll wrap it up with some results, and should be done. So to get started, I want to talk about the need for on-chip networks, or network on chips, or sometimes we call them a NoC as well. So this graph here is just showing on the right side, this black line shows the increase in CPU processor speed. And I mean, this is for specific processors, but generally speaking, from about the 70s up to the early 2000s, you were seeing this really rapid growth in your processor. So what that meant was that every year, if you were Intel, you could just ship a processor that was twice as fast, and it still only had one core. In about 2002, we hit limits on that. And due to silicon, you can't really scale the clock speeds anymore. And so then we started adding more cores to our CPUs. So this presented a problem because all of your cores on a CPU need to communicate. They might be sharing memory. They might be sharing other resources as well. And the traditional communication architecture is a shared bus. So on this bus, you have all these PEs. These are processing elements. So these are your CPU cores, might be a shared memory cache, or today might be an AI accelerator. And then each of them have an interface to the bus. And if processing element 0, for example, wants to communicate with processing element 3, it's going to request exclusive access to the bus and then send information to it. And as we can see, as the number of cores grows, this shared bus really starts to slow down your chip. So instead, researchers developed these on-chip networks, which are a highly parallel method for communicating on multi-core systems. So in our example here, we have a 4-node system, and each node is a router, and each node has a processing element as well. And now we can have this more parallelized and sometimes asynchronous communication between each of our nodes. So specifically for our work, we look at a specific network topology, which is a 2x2 square mesh, or sorry, not 2x2, an n-by-n square mesh. This would be a 2x2. And in that mesh, we have these routers, and the routers are just in charge of routing packets through the network and determining where they go. We have the processing elements, which, as mentioned, they introduce new packets into the network. And then in between routers, we have these links. And so each link is made up of a channel, which is this arrow here, and that represents a physical wire. And on a wire, we're saying that a packet is sent across it during one clock cycle. And packets are sent across wires into these input buffers. So each router has 5 input buffers. They're not all shown on this diagram, but they'll be shown later. But it has one in each of the cardinal directions, and then one for the processing element. But these buffers are first in, first out hardware queues, where a packet is pushed into the back of the queue and then popped from the front to be used. And that's how packets are moved over those links. So the mechanism that a network on chip works is through packet switching. So processing elements generate new packets. They'll push them into the local queue of each router. And then the router will look at all the packets at the front of each of its queues. It will select one, pop it from the queue, send it across the channel towards its destination. So in our model, we use a specific methodology called XY routing. So this is super simple. First, packets travel horizontally across the network, and then they'll travel vertically. So for example, if processing element 0 wanted to generate a new packet, if it wanted to communicate with processing element 3, it would generate a new packet. The packet would be sent horizontally to router 1, and then vertically to router 3. And this is really simple. There are a lot more complex routing algorithms available that do dynamic routing or fault detection. However, those are a lot harder to implement on actual hardware. And so in a survey of real-world network on chips from the past couple years, about 40% of them used a variant of XY routing because it is sufficiently simple to implement on a network on chip. Additionally, it's known to be deadlock-free, and it's also deterministic, which are all great things for easing verification and hardware design. So the last thing that the routers do is they have to arbitrate between different packets. So if you have several packets that need to use the same channel, the router chooses which packet to send first. And again, we just use a relatively simple round-robin arbitration, which is kind of a priority queue based, just to ensure fairness among all the packets. Again, there are more complex implementations that you can do, but because we're implementing this network on hardware, oftentimes a simpler implementation is used to be able to describe the circuit that does that. So we'll talk about what we're going to verify with our network on chip model. So we're looking at power supply noise. So this is voltage drops and spikes in the network. And this noise is caused by traffic in the network, so either high traffic or high changes in traffic. And these spikes and drops can lead to erroneously flipped bits in the network, which can lead to dropped packets, corrupted data, or just in general, an increased latency. So this is a diagram from one of our collaborators, and it just shows that as the process node or transistor size shrinks, the overall peak power supply noise voltage goes from about 40% in this on a 32 nanometer node to about 14 or 80% on a 14 nanometer node. So if you're seeing these spikes that are about 80% of your average expected power, you're going to have this corrupted data. And we want to be able to provide upper bounds to this. So our contribution for today is we provide a modular network on chip model. That model is the NoC I previously described. It's written in the Modest language, which I'll cover more in a second. We talk about CTL model checking for the correctness of the model. We talk about the replication of results from previous models. And finally, we'll look at power supply noise characterization for network on chips up to an 8x8 mesh. So we'll start with our modeling approach. So power supply noise is highly dependent on both the network on chip implementation as well as the traffic patterns that you see in the network. So network on chips are tightly coupled networks. So the behavior of a node in the network is highly dependent on the behavior of its neighbors. And it's really hard to separate out a node from its neighbors and analyze it by itself because of that really tight dependency. So modeling power supply noise requires the right level of abstraction when looking at a network. So we think that the correct level of abstraction is to include all the routers so that we can model the tight coupling across the network, but not to include all the circuit details. And given that, there's three kind of general approaches to modeling power supply noise. So there are semi-formal approaches that use a combination of simulation and based typically on the behavioral model of the circuit that is then synthesized into a power level model. And these can provide maybe interesting results and potentially some bounds on the power. However, the simulation often cannot provide any kind of statistical bound because you just can't do enough runs with the simulations. So some previous formal approaches were a monolithic style 2x2 mesh network on chip written in the Modest language. So this was the inspiration for our work. This network on chip kind of showed a potential power supply noise characterization method, and it also showed that generally this abstraction seems to be feasible in Modest. However, it wasn't scalable, and a 2x2 network is really small. Typically, you're going to see networks that are at least bigger than 6x6 to accommodate all the cores and caches and stuff on a chip. So our approach is a modular network on chip, again, using Modest. So a quick aside about Modest. So Modest is a probabilistic modeling language, and it is a high-level language in the sense that it provides to you high-level constructs such as parameterized processes and functions and high-level data types. And then it takes your high-level data types and processes, and it can convert them into an underlying representation. So for our case, we use a DTMC, or a discrete time Markov chain, as our underlying representation. But Modest can do other things such as MDPs or CTMCs, but we don't need to use those. Oh, and the reason that we chose to use Modest as opposed to a tool like Prism, which is another probabilistic modeling language, is that Modest has really rich support for data types, as we'll see in a little bit. OK, so let's look at how we characterize power supply noise. So this will introduce the properties that we use to characterize power supply noise, and then we'll show how that applies to our model. So there are two main components of power supply noise. So there's resistive noise. So this is relative to the inherent resistance of any circuit. All circuits have some level of resistance, even just wires do. And additionally, it's relative to the current at any time in the circuit. So inductive noise, on the other hand, is relative to a change in current over time and the inherent inductance of the circuit. So based on some previous work by our colleague, we can abstract resistive noise in our model to be relative to the current cycle activity, where the activity is defined as the number of packets sent or received during a clock cycle. And additionally, we abstract inductive noise to be the change in packets over 2 clock cycles. So if you send 5 packets on clock cycle 1, that would be your resistive noise for clock cycle 1. And if on clock cycle 2 you send 2 packets, that change would be an activity level of 3. So then with those activity levels, we'll use probabilistic computational tree logic on our DTMCs with bounded reward properties to measure the power supply noise over a set of clock cycles. And so the first thing we do is we aggregate the noise, which is router specific. We aggregate it all into a global count. We have 2 counters, inductive and resistive. And so every time any router exceeds an activity threshold, we increment one of those counters for the noise. So then once we have those global counters, then we calculate our properties of this form, which is stating that we're looking at the probability that within m clock cycles, the noise, or the count of noise events, is greater than or equal to k. And so here on the left, or on the right, what we're looking at is an example of k is 1, 5, or 10. This is on a 2x2 network on chip, and this is the inductive noise. And so we can just see these sweeps. Oh, and this is a CDF, I guess. As we sweep over the number of clock cycles, we can see the probability of exceeding this number of noise events just increases over time until eventually we'll reach 1. OK, so now that we kind of know about power supply noise, we can talk about how the network on chip is modeled in the Modest language. So we define a n-by-n network on chip as the parallel composition of n-squared router processes, the Modest language. So for a 2x2 network on chip, it would just look like this, where we're taking 4 routers, and we compose them in parallel along with a clock process, which is what we use to track the elapsed time. And this is kind of our first look at the Modest language. So here we're declaring a parameterized router process. It's parameterized by an identifier. And then here in a parallel block, we're composing 4 of them together. So just as a quick review, the components that we see in a router, or we have the 5, each router has a processing element. And then we also have our 5 buffers in the cardinal directions and the local buffer, along with our 5 channels. And those make up the links between both the processing element as well as the neighboring routers. And then additionally, we have internal logic for routing and arbitration. And so the execution of a router in Modest is modeled by the serial composition of several processes that define that routing and arbitration behavior. So what that looks like is like this, where we just have the semicolon is the serial composition operator in Modest. So we just compose in serial all these sub-process calls They're all parameterized by the identifier. And then this last recursive call to router is how we simulate infinite execution in the model. Or I guess how we model infinite execution. So briefly, we'll touch on why we use these router identifiers. So these router identifiers, because we have this fixed regular mesh, we can go from an identifier into coordinates, and then we can go from coordinates back to an identifier. And so this provides us a great way to modularly define both the traffic patterns that we want to measure, as well as if you want to define like router-specific routing algorithms, you could use this as well. And then additionally, the network on chip state is just stored as a global array where each router is just an element in that array, and we can index it into it by the identifier. So let's talk about we'll look at one of the process sub-process calls. So look at generating packets. So the generate packets process models a processing element connected to a router. And so it injects new packets into the network. And it's a primary source of probabilistic behavior for the model. Actually, it's the only source of probabilistic behavior for the model because you determine probabilistically both whether or not you will inject a new packet, and additionally, you have to determine where that packet is going to be sent to in the network. So this is kind of a quick sketch of what the process looks like. If the local buffer is full, we're going to do nothing. Otherwise, based on some probabilistic condition, we will send or we'll add a new packet to the router with a probabilistic destination X. And in our work, we just use a uniform destination because there's not a lot of work on what real-world packet distribution looks like in network on chips. We won't cover the rest of the sub-process calls, but you're welcome to look at our paper for in-depth look at them. But as a quick basics, we have this prep router sub-process. This sets some state flags so that we can maintain a synchronous update. Advanced router actually sends the packets. Update priority is how we handle arbitration and fairness. And then update global noise tracking is how we measure power supply noise. Then the last thing that we haven't talked about is this next clock cycle. And this is a synchronizing action that we'll cover more in a second. So the clock process just looks simply like this. And the clock process is in charge of controlling the stepping of time, or clock cycles, in the model. And so how we do this is through a reward, transition reward in the underlying DTMC. So a transition reward works by, on a specific transition, in this case, the next clock cycle transition, we just set this reward to be equal to 1. And then what we can do is we can just take a summation of that reward over the execution of a path. So in this path, for example, we have 2 next clock cycle transitions. So on those transitions, the sum of the reward will increment by 1, and we'll move through there. So then if we use this bounded eventually with the sum of the reward here, we can correctly calculate our bounded properties. OK, so then the next thing we'll look at is some of the CTL properties that we verified. So some of the basic properties is we looked at verifying that there's no buffer overflow. We're modeling hardware buffers. And so while in the model, the Modest language supports arbitrary length arrays, we don't want to exceed a maximum size that we've specified. We also want to ensure that each channel is only used once during a clock cycle. As for digital circuits, each wire can only be driven once during a clock cycle. We want to ensure that all the packets that are generated are correct. And we also want to ensure that our priority list is valid. So when we first went to implement these CTL properties, we ran into issues with the modular model seeing a much greater state space than the original monolithic model, or the old concrete model, for a 2x2 network on chip. And this was concerning because we really wanted this to be a scalable model. So the reason that we were seeing this expanded state space is between semantic differences between our network on chip model and the Modest language. So Modest is based on an asynchronous process algebra, whereas NoC, or network on chips, are modeling a synchronous digital hardware. And so as kind of a quick demonstration, this on the right is just showing the digital hardware, where we have all of the updates happening synchronously on the rising edge of the clock. Whereas here, we have the Modest execution model, where you have to explore each update independently because it explores all those interleavings. So our end goal is to actually eliminate these interleavings because for a digital network on chip model, they're not really interesting for us. And additionally, another issue that we saw before we fixed this synchronization issue is that if we look at the previous work of the monolithic 2x2 model, our modular model, when instantiated with a 2x2 network on chip, produced really incorrect power supply noise results. And so we wanted to fix those. So the way to fix that is that we introduce synchronizing actions, which are available in both the Modest and Prism languages, and they kind of act like an action in a label transition system. And we introduce these actions into all state updates so that all the state updates that we care about happen synchronously across every instantiated router in the network. And doing so, this just really reduces the state space that we're looking at. So we'll skip that example for now. But this is a quick look at for CTL model checking our 2x2 network on chip. So the asynchronous original version that we implemented without any synchronizing actions, we ran out of memory at about 126 gigabytes after a little bit more of a day of model checking. And composed to our synchronized model, we were able to do the model checking in about 10 minutes and use about 10 times less memory. And additionally, implementing these synchronization actions resolved our expected power supply noise with the modular model when instantiated for a 2x2 network on chip now matches the behavior of the monolithic model. So if we want to look at some of our results, we were able to instantiate 3x3, 4x4, and 8x8 network on chips. And while on their own, these results aren't particularly interesting. We can see the expected use case here where as we get into larger network on chips, the power supply noise, the rate of change of the noise is much greater for larger network on chips. And this just occurs because in this global measure, we see more packets overall in a larger network. And so additionally, we have another measurement strategy where we're looking at individual routers in a network. So in a 3x3 network, we have 3 types of routers. We have corner routers, edge routers, and a central router. And in this case, we've been able to generate these power supply noise CDFs for each type of router in the network individually. And because we have a little bit of time, we'll look at, I wasn't sure if we'd get here, so look at some future work that we're looking at doing. So we want to characterize power supply noise for different traffic patterns. There's some recent work late last year in a survey of traffic patterns in network on chip. A survey like this hasn't really been done before because networks on chips they are so different across the industry in terms of their use cases. But since they've been around for a long time now, they have enough information to do this survey. So we'd like to implement some of those findings in our model. We'd also like to use simulation level results to relate our abstract model back to a more concrete measure of current and voltage. So previous work had showed that the power supply noise can be abstracted down to just the activity level of each router, and we want to be able to go in the reverse and potentially provide a real current value of upper bound. And then the last thing that we'd like to do is develop potentially an abstract router for verifying larger networks with CTL model checking. And that's all. Thank you.
So, any questions? No? Last chance in VMCAI. Okay, good.
Thank you. Now, how do you think how hard would it be to use this for different types of NoCs, for example, octagon and so on, the different layouts?
Yeah, so we have considered some. We actually because originally we restricted it to a square mesh style network on chip, but it works for rectangular ones. To transition to different ones like an octagon or rings or anything like that, it would require some model changes in terms of the data structures used, because our data structures are based on having 5 buffers and 5 channels. But I think it should be relatively possible in the Modest language.
Okay, thank you.
Mm-hmm.
More questions? Okay, so let's thank Nick again. Yeah, let me also thank the organizers, the Thomas, and the